Bismillahirrahmanirrahim. Welcome to the lab for the course Fundamental of Physics. Experiment number 8, parallel plate capacitor. You might have come across a small or big type of these devices. We call them capacitors. You see, all these are the capacitors here, and you might have seen in many of your devices, especially the old electronic devices. Now mostly you have chip, by the way. And this is the basic idea of the parallel plate capacitor, that you have two conducting plates, one this plate and the second this plate, two conducting metals, two conducting conductors, plates, parallel, of any shape, maybe square, maybe rectangle, maybe triangle, whatever. And right now you are looking two circular conducting plates placed parallel with each other and with some distance between them. So this is the distance between them, this is d distance between them. Right, and the plates having some area A. Okay, what are the objectives of today's experiment? To study the dependence of a capacitor, of a parallel plate capacitor, on the separation between the two plates. As I told you, you'll be having d distance, or the separation between two plates. What happens, we will see today what happens when we change the distance separation between the two plates. To determine the electrical permittivity of free space, you have to find out this one. We have the real with us, the standard or the actual, and you will do your experiment, you will calculate, you will determine the permittivity for the free space, and then find the percentage error. To study the effect of placing a dielectric material between the plates of a capacitor to determine the dielectric constant. So dielectric constant, what do we mean by all these terminology? We will discuss one by one, don't worry. Now, the apparatus you need, you have first of all this parallel plate capacitor. So this is number one parallel plate capacitor. These are two conducting plates which are separated by a distance d between them, and they have area A. If you measure with the ruler, for example, from this point to this point, and that cross, your ruler must pass through the center of this plate, you can remove this plate from the apparatus and you can easily measure the diameter. So this is your capacitance meter. This is your capacitance meter. Normally it is a digital multimeter, but when you see this one, what is this? This is CAP, cap means capacitance. So once you bring this selector switch to this cap position, so you'll be able to measure the capacitance of the capacitor. These two leads here you will connect. Okay, then dielectric material. Right now you see here nothing in between these two plates of the capacitor here, only air in between the plates. But in the second part of today's experiment, we'll be inserting some dielectric material, wood or acrylic or any insulating material. We call it the dielectric material. So this is your dielectric material. We'll put it here inside. Then you need connecting wires. These connecting wires, this you see blue and red, these are the connecting wires. Okay, right. What is the theory behind today's experiment? The basic idea. First of all, parallel plate capacitor. What is it? It is an electric or electronic device used to store electric charges. Okay, it is an electric device that is used to store the electric charges on its parallel conducting plates. Okay, in electronic and electrical circuits, we use it as filters, smoothing filters. As filter we use it sometimes, and in electronics, sometimes when you're using many electronic devices and you get some output signals, so sometimes you get noise which is not required at the output level. So to remove those noise signals, we use capacitors in combination with some other devices to remove those signals so that you get good quality output signal. Now, you see, whenever you connect a parallel plate capacitor with battery, okay, for example, you have this one terminal of the capacitor, you connect it with the battery, or right now I'm connected with the capacitance meter, so it's using its battery, by the way. And this is the other terminal, we connect it with the other terminal of the capacitance meter. What happens in the beginning? There is a zero charge on the plates of the parallel plate capacitor, but gradually the charges starts gathering on these two plates. Okay, so if I say Q is the amount of charge on the plates of a parallel plate capacitor, the unit is coulomb, and V is the electric potential which is built across the two plates of the parallel plate capacitor. Then the experiments show that voltage is directly proportional to the charge, amount of charge gathering on the plates. Okay, and this gives you Q is equal to some constant, let's say C multiplied by V. So this further gives you C is equal to Q over V in the unit of farad. Farad is the unit for capacitance. So this is capacitance. You see, C is a constant. We call it capacitance or the capacitor. Capacitance or the capacity of the capacitor. I mean, how much amount of charge you can store on its plates. So that is the capacitance or capacity. Now, how can we increase the capacity of the charge of the capacitor? For example, if we have the lab and we have a space or the capacity for 18 students, for example, how to increase the capacity of this physics lab, for example? I would say, okay, we have these three tables which are spare, free, not used for a long time, so we can remove them from the lab and we can set another table for 3 more students. So instead of 18, I'll be able to accommodate 21 students. So I'm increasing the capacity of the physics lab, for example. Similarly, if we talk technically about the capacity or the capacitance of the capacitor, so that I need to store more and more charges, there is a limit for, as I told you, there is a limit for the capacity of a physics lab, that 18 students in general. So if you need to increase, you have to do something like I gave the example. Similarly, there is a limit, maximum charge limit to store on the capacitor. So if you want to increase, but again there will be a certain limit even if you increase, not unlimited capacity or the capacitance. So the capacitance C is directly proportional to the area. If you replace the plate of a parallel plate capacitor with a greater area, larger area, you will be able to store more charges. And similarly, if you decrease the distance between the plates, you will be able to increase. So you see, if you increase the area, you will increase capacitance directly proportional, as you see. And if you decrease, inversely proportional, capacitance C is inversely proportional to the distance between the plates. So it means that capacitance will be increasing if you decrease the distance between the plates, so inversely proportional. If I write some constant equal to some constant epsilon, this is Greek letter epsilon, epsilon 0 or epsilon naught, A over D, right? Further, I can write as I told you, this epsilon 0 or epsilon naught is the permittivity of the free space. Okay, right. So it will give you, I can write C multiplied by D is equal to epsilon 0 or epsilon naught A. Right. Now I'm going to write in terms of the slope, so that I would draw at the end slope graph and find the slope to find this value epsilon 0 or epsilon naught. I have real, but I will find it with the help of the experiment. So I can write this C divided by 1 over D is equal to this. This will finally give me epsilon naught is equal to, I take this A to the other side area, I would write here, and this is C divided by 1 over D. So this is area. You simply need to find out the diameter, and 1 by 4 pi d square will give you the area. So this is slope. Okay, where slope is equal to C over 1 by D. D is the distance between the plates and C is the capacitance. Right? Right. So this is your real value. Okay, 8.85 into 10⁻⁻12 farad per meter is the real value. So this is all about, you need to write in the theory, for example, in the lab report also. This is the ultimate thing you would be calculating, keep in mind. And yes, now you see meanings of some physical quantities. As I told you, electrical permittivity, it is capability of a vacuum to permit electric field lines to pass through some, some surface like this parallel plate capacitor. This is the real, as I told you. And dielectric constant, a quantity measuring the ability of a substance to store electrical energy in an electric field. So as I told you, we use some dielectric material, which is in fact an insulator, and we will calculate. So this is the capacitance once you have some insulating material in between, I mean the dielectric, and this is C0 is without anything in between, simply air in between the two plates. And the dielectric material, as I told you, electric material, which is an insulator that can be polarized by an applied electric field. What does it mean? It means that if you have any material, you have a mix of positive and negative charges, but once you bring it near some electric field, for example, if this is the negative field on this side of this plate, for example, the positive charges will be attracted by this. So you'll be having positive charges here and negative charges on the other side. This is what we mean by polarization. When we bring some dielectric material near to the electric field, the charges are polarized. The material is polarized. Pole means side. One side positive, one side negative. So it is polarized, arranged properly. All right. Now you have effect of dielectric material. As I told you, when we insert a dielectric material in between the plates, the capacitance increases. So this is the capacitance when you are adding, Cx mean when you are adding dielectric material in between the plates. It increases by a factor k, where k is a constant. We call it dielectric constant. So we get like this one. It has no unit because farad will be cancelled. This is the second part of the experiment you will be doing. As I told you, you can measure the area if you measure the diameter. Okay, you have for example the circular plate. You measure the diameter. I mean the line should pass through the center. So this will be your diameter, and half pi d square. If you measure in centimeters, you will convert it into meter later on. Okay, and connect the parallel plate capacitor. So this is part A of the experiment, and you have table 1 for that, and you have to change the distance from 2, 4, 6, 8, 10 millimeter every time. You can have 5, 10, 15, 20 if you are comfortable with it, and read the capacitance for each changing distance. And table 1 you have to complete. Similarly for table 2, I will show you how to. Now this is the first part of the experiment, and as I told you that you have to start from any distance. What I did for you in the lab, I did it, for example, I start from 2 millimeter, right? So 2 millimeter, right? For example, I write it here D in millimeter, for example. Okay, here I use 2, 4, 6, 8, 10, 12 and 14 millimeter, right? Then I would convert it into meter, because 1 meter is equal to 10 raised to the power minus 3 meter. So I'm writing it here, so I have to write it here. So 2 multiplied by 10 raised to the power minus 3, 4, 10 raised to the minus 3, 6, 10 raised to the minus 3, 8, 10 raised to the minus 3, okay, we always use SI units. So this is 1 by D. 1 by D mean I give you one example, remaining you would do by yourself. 1 divided by, and what is your answer, you would write down here. Okay, similarly, what is 1 divided by 4 minus 3, the final number you would write down here. Similarly, you will be having all these numbers here. Okay, you need all these things because you need 1 by d in the graph I just finished with you, and this is the capacitance. Initially you have to measure this distance in millimeter, and this is the capacitance, right? Now what I measured for you, the capacitance 0.210 nanofarad. Nano mean 10 to the minus 9. Whenever you do the calculation, you have to use this 10 to the minus 9. Then for 4, for example, I have this reading. Okay, for 6 I have this one. For 10 I have this much. For 12 I have this one. For 12 I have 86. This one I have 86. Okay. For 8 I have 86, and for 10 I have 0.080, not this one. Right, and then for 12 I have, and then finally I have, okay. And please, you will this is the work for you. You will be completing all these calculations, and you know, I told you that you have to move one plate. You see, this is your experimental arrangement. So these are the 2 plates, and this is the distance between the plates, d. One plate on the left side is fixed. You have to move the right side only. You see, this is the scale here, okay, in centimeter 1, 2, 3, 4, and further divided into smaller lines. 1 centi is equal to 10 milli. So if we select the cursor of this plate at 0, then we start, for example, from 2 millimeter, and then we keep on sliding it on the right side, and you'll be getting new distance, and for every new distance 2 millimeter increase, you will be getting all like this one. Okay, so this is 2, 4, 6, 8, 10, 12, 14 milli, and for every, whenever you change the distance, you look at the capacitance meter and you will note the reading, and you will complete your table like this one. Okay, and then you will draw a graph for this, as I told you, you need a graph between this side you have 1 by d, and this side you have c. If you go back, what I did with you, yes, this one, okay, here is your slope, which is c divided by, so what does it mean? Normally slope is, this is del y by del x, right? Del y by del x is your slope, right? So it means along y-axis you have to take capacitance, along x-axis you have to take 1 by d. This is what I am doing it here in the graph. Okay, right. And for the graph, you see how to select the scale. For example, this is C. Normally you have 0.210, 0.120 all multiplied by 10 raised to the power minus 9. So if I write here for all 10 raised to the power minus 9 farad, and here it will be difficult for you to select the scale in points. What I do, I multiply by 10 raised to power, you see, minus 2, so that you will shift this decimal to 2 more points. So it will be like 21, it will be 12, it will be 9.6, it will be 8.6, it will be 8, it will be 7.3, it will be 6.9. But now you'll be multiplying with what? With, in fact, 10 raised to power minus 11 farad. Keep in mind. Now, you see the smallest number here you have 6.7, and the maximum you have 21. So if you have the centimeter scale, you need, for example, okay, 2, 4, 6, 8, 10, 12, okay, 14, 16, 18, 20, 22. So up to 22 will be okay, because maximum reading with you is 21 and the minimum reading is 6.7. But don't forget, you will multiply with, when you are doing the calculation, with 10 to the minus 11. For example, this is your 21, and here you would write, for example, 50, 100, 150, 200, 250, okay, 300. So here you'll be having 400, and here you'll be having 500. So up to 550 or up to 600, you can keep it on the x-axis. For example, if you have this one 6.7 and this one you can calculate, you will mark, okay, and you will write down here. So you select all the points here, and then you will draw a graph and you will find out the slope, okay, del C over del 1 by D. This slope you will be using for the calculation of the unknown permittivity. Okay, unknown in the sense you are going to calculate. This will be slope divided by the area. Okay, I told you how to measure, how to calculate the area. You simply need to measure the diameter of the plate, okay, and then use the rule area is equal to 1 by 4 pi d square. Okay, okay, pi d square, this is the area, and here you will use the area. Okay, now the second part of the experiment, what you do, you select different materials. You have some the rectangles of some thickness you can measure with the ruler or with the vernier caliper, but I am giving it to you now. First of all, we have paper, then we have acrylic, like glass, transparent material, and then we have wood, khashab. Thickness, for example, I have in millimeter, okay, and capacitance, this is in farad, capacitance in farad. Okay, for example, I have first of all this paper, white paper of this thickness 0.40 millimeter. Once, like experiment number 1, what you did before, there is air in between the plates, and there is dielectric here. Any dielectric means these materials are dielectrics. Okay, now when you have air in between, first of all you put it the dielectric and measure the capacitance from the capacitance meter. For example, what I measured 0.290. when I remove it, I have only air in between, so it will be less. Okay, and then I change the material with the acrylic, with the transparent material, not the glass, 1.95 its thickness. When I measure the capacitance from the capacitance meter, this much, and when I remove the dielectric, I get 0.141. Okay, and for the last one, the wood thickness, I am taking 2.9, all in millimeter, right? And the capacitance, when I insert the dielectric material, I mean the wood right now, it would give you, for example, this one for me. You may have different due to certain other parameters and the sources of errors. Like this one. This is nothing. Dielectric constant K is equal to Cx over C0 or C0. Okay, Cx this one, and C0 this much. Okay, you will calculate by yourself, please. Right? Now, as I told you, I already measured for you the diameter. Okay, diameter I measured for you 17.7 centimeter. So 1 meter is equal to 100 centimeter. So you divide by 100 and you would get 0.177 meter. So you use this value over here, and then you will calculate final area. Okay, and slope of the straight line graph, here you would write down, as I told you, how to find out, and then slope divided by the area, you will get this one. And as you know, I gave you the real or the actual 8.85 okay, this is the real. Okay, so this is real. Okay, real, and this is the calculated. You calculated your result, this one, and you will find out the percentage error. The precautions, what things you have to take care of. Plates of the capacitor must be parallel, and we have some setting there, so with the screws you can go for horizontal and vertical settings of the plates. Connectors must be properly tight, no loose connection. Distance between the plates must be measured accurately from the scale on the parallel plate capacitor apparatus. Thank you very much, and have a nice day.